Hello there. In this video we're going to talk about another rule that can be used to approximate the probabilities of distributions of random variables. In the previous video we discussed what we called the empirical rule, which said that if you have a distribution that is normal or approximately normal, you can approximate the area within some standard deviations from each other. So if this is, for example, mu minus sigma and mu plus sigma, then the area between them is going to be approximately equal to 68%. If you want to go to two standard deviations from the mean, then the area is going to be approximately 95%. And if you want to go within 3 standard deviations from the mean, that's going to be approximately equal to 99.7%. So in this video, we're going to be looking at distributions that are not necessarily symmetric or not symmetric at all. For example, you can have some distribution that looks like that for the discrete variable case, or you could have something that is extremely continuous and not normal at all. So we'll discuss a theorem that is used to approximate the probability that you're within some standard deviations from the mean of non-symmetric distributions. So the theorem that generalizes these approximations is what we call Chebyshev's theorem. So Chebyshev's theorem. Some people call it Chebyshev's inequality. And it says the following. So the probability that the absolute value of x minus mu is greater than or equal to k sigma is always less than or equal to 1 divided by k squared. And this is for any random variable x who has some distribution, whether it be discrete or continuous. We're not going to prove this result as it requires some additional tools that we're not going to discuss quite yet. But the really important property about this theorem is that you do not need to know anything about the distribution at all. You don't need to know the mean, the variance, or the distribution itself. This is true for any random variable x with some probability distribution function. So let's take a look at this inside value to sort of get a better understanding of exactly what this theorem says. So let's do some pre-calculus analysis of this expression. So let's look at x minus mu is greater than or equal to k sigma, and let's see what types of x values actually satisfy this. So solving absolute value inequalities, we're going to split this up. So this is going to be x minus mu is greater than or equal to k sigma, or x minus mu is going to be less than or equal to negative k sigma. And now I'm going to add mu to both sides of this equation. So plus mu plus mu. So we're going to get that x is greater than or equal to mu plus k sigma, or x is going to be less than or equal to mu minus k sigma. So let's look at a number line. So this is going to be mu. So let's assume we choose some value of k, so this is going to be mu minus k sigma. This is going to be mu plus k sigma, so we're going to assume that k is some positive number. And of course, if k is equal to 0, then you're directly on top of the mean, so we're going to assume that k is not negative. So pretty much what Chebyshev's theorem says is the probability that x minus mu is greater than or equal to k sigma. So in terms of this picture, we're talking about all x values over here. So if we're inside of this blue region, then the probability that that occurs is going to be less than or equal to 1 divided by k squared. So this does not give you an approximation of what the value can be. It gives you an upper bound on what the probability can be. So it gives you a set of values that it could be, not an approximation on the exact value. So let us create a more simple way of stating this. So I'm going to be talking about this interval here. So I'm going to call this interval ik. So ik is going to be defined to be the interval mu minus k sigma and mu plus k sigma. So that means Chebyshev's theorem says that the probability that a random variable x is in or not in this interval is going to be less than or equal to 1 over k squared. So that's what Chebyshev's theorem says. So let us also look at the complement of this. So what is the probability that x is going to be within this interval? So that's going to be greater than or equal to 1 minus 1 over k squared. So that the probability that you're within k standard deviations from the mean is always going to be greater than or equal to 1 minus the reciprocal of the square of the number of standard deviations that you're interested in. So let us look at a couple of examples in detail. So let's consider the smallest integer value of case. So let's assume k is equal to 1. So what is the probability that x is not within I1? So what do I mean by I1? So I1, so this is going to be mu, this is mu plus sigma, and this is mu minus sigma. So what is the probability that you're in this yellow region? Discrete will include these points, and so will continuous, so no big deal there. So the probability that you're not within this interval from Chebyshev's theorem is going to be less than or equal to 1 divided by 1 squared, which is equal to 1. Now this is an extremely trivial case because we know that the probability of any event is always between 0 and 1, so this is a trivial statement. And of course, the complementary version of this, so the probability that x is within this interval, 1 standard deviation from the mean, is always going to be greater than or equal to 1 minus 1 over 1 squared, which is 1 minus 1, which is 0. Again, this is a trivial statement because we know that the probability of any event is always greater than 0. So Chebyshev's theorem actually does not make sense for all values k equals 1 and also between 0 and 1. So in general, it doesn't really tell you anything for k values in the interval 0, 1, or 0, 1 inclusive. So let's look at the first integer value that actually is useful. So let's consider the case for k is equal to 2. So we have some distributions, not necessarily normal. We do not know. So let's assume the mu is there. So there's mu minus sigma, mu minus 2 sigma, mu plus sigma, mu plus 2 sigma, for some mu and sigma. So what is the probability that you randomly select an x value and it is in this region? Well, we don't necessarily know the distribution if we haven't really developed the model for it. So getting approximations or bounds on that area is extremely useful. So Chebyshev's inequality states that the probability that x is not within I2, so I2 is this region in the middle, is going to be less than or equal to 1 over 2 squared, which is 1/4. So the probability, or the area shaded, so let's assume this area here added together is A. So we have that A must be less than or equal to 1/4, or 25%. So that means we do not need to consider 75% of the population when we do this study, which, is a good approximation, especially if the population is large. And we can also look at the complement of that, so the probability that x is within 2 standard deviations from the mean for any distribution is going to be greater than or equal to 1 minus 1/4, which is going to be 3/4. So the probability that you're within 2 standard deviations of the mean, so this area here, which I'm going to call alpha, so now we know that alpha must be greater than or equal to 3/4, whatever that area is. So similarly, we can consider for k is equal to 3. And remember, you don't have to choose integer values. You can say k is equal to 2.5, 2.85, and so on. So the probability that x is not within 3 standard deviations, according to Chebyshev, is going to be 1 over 3 squared, which is 1 over 9. So notice, if we go 3 standard deviations out, so 1, 2, 3, 1, 2, 3, we're covering a lot more of the distribution. This is actually a misleading graph. So let's draw a more appropriate one. 1, 2, 3, 1, 2, 3. Let's put 3 here. So this area here. So notice as we go out of the standard deviations, as we increase the number of k, this area is going to be extremely, extremely smaller than the previous k value, regardless of the distribution that we have, because most of the data is going to be centered around the mean. So this area here, so this area value, is going to be less than or equal to 1/9. So this area value is going to decrease and converge to 0 as I make k extremely large. So this Chebyshev's inequality at least matches that intuition. And if I'm interested in getting a bound for this probability in green, which I'm going to call alpha again, so the probability that I'm within 3 standard deviations is going to be greater than or equal to 1 over 9, which is going to be 8/9. Which is, let's see, what's that equal to? 8 divided by 9. So it's about 88.9% chance that you're always going to be above. Remember, if we're in a symmetric distribution, we already know that this is equal to 0.997. So this is at 88.9. So this is true for any distribution at all. This is what the empirical rule said for the symmetric or normal distributions. But this bound, remember this is not an equal sign, this is a greater than or equal to sign. So for any distribution, regardless of the shape, this area in green is always going to be greater than or equal to 88.9%, which is an extremely strong property, especially if you do not know anything about the distribution at all. And that is what Chebyshev's theorem states, and it's really useful in the field if you want to get a general idea of pretty much any distribution if you're not quite sure whether it is a normal distribution or whether you have no idea about the distribution at all.